Hey class, this is chapter 16, acids and bases. So we're going to continue on with our equilibrium work, but here's our first chapter where we talk strongly, very in-depth about acids and bases. So let's first take a look. Some definitions, this is in the 16.1 where it talks about the history of the acids and the bases. This guy's name is Arrhenius. He came up with a substance that dissolves in water, increases the concentration of hydrogen ions. So that would be something that looks similar to this, where if I throw this substance in water, what we get is a breakdown where it splits into H plus and Cl minus. Like 100% of the time this happens, so there's no HCl left. It is all H plus Cl minus, and if you increase this concentration, then it is an Arrhenius acid. The base is the same thing, except when it dissolves, it increases the concentration of hydroxide ions. Okay, so that would be similar to showing you this happening. And obviously, if that increases, then we have an Arrhenius base. So this is a very simple and very basic definition of an acid and a base. And it did not stand the test of time so well, so we moved on to what's called the Bronsted-Lowry. Let me just go one more here. Bronsted-Lowry said, look, if it donates a proton, then it is a Bronsted-Lowry acid. And here's what it looks like to donate a proton. So we start off with our same acid, hydrochloric acid. This time, though, I add it to water, and then what you see then on the other side is the H part, the H plus, coming off and attaching to water to give us something called the hydronium ion. So if this H is donated to water, then what's left behind then is the negative part. Okay, so that would be, in this case here, you would see that this right here is the acid. It's the acid because it donates a proton, an H plus. This would, of course, be the base then because it actually accepts a proton acceptor. And when it accepts the proton, then it becomes the hydronium ion. Okay, so when you increase the hydronium ion concentration, then you have an acid. And then, of course, we have the Cl minus that's left over. Now, you're going to see terminology in the book that says if this is the acid here, that means that this then is the conjugate base. That conjugate just means the other side. It means like the thing that has changed into a base. And that means that if this is the base, then what I have over on this side is the conjugate acid. So these are like a pair where the base and the conjugate acid are together in a pair, and the acid and conjugate base are together in a pair, which is why I have the arrows drawn like this. So they are like related to each other. Okay, so when I talk about, I'll ask you at some point, what's the acid conjugate base pair? And if I ask you that for this example, it would of course be the HCl, and the Cl minus would be your acid conjugate base pair. Okay, moving on. Must have a removable acidic proton. That's a must for a Bronsted-Lowry acid. A Bronsted-Lowry base must be able to accept a pair. And how does it accept, accept a proton? How does it accept a proton? With a pair of non-bonding electrons, which is how water does it. So you guys know that H2O, if I draw it out, H2O looks like this. It's got H, OH, and oxygen has 6 for its Lewis structure. So I start 1, 2, 3, 4, 5, 6, like that. 2 are paired like this, and 2 are single, like that. So the singles go to the hydrogens, but then when we have, that's a plus, believe it or not, HCl, that H comes over here as an H plus, which means it does not have any electrons. So it's got 1 proton, 1 electron when it's neutral, but hydrogen with a plus means no electrons. So here is where it attaches itself here to those two. That's how a Bronsted-Lowry base accepts a proton, is that both of these electrons right here are supplied a bond, which is called a conjugate bond. No, that's not it. I forget what it's called. We'll talk more about that later, though. So if you have a molecule that can be both an acid or a base, then we have what's called amphiprotic, which means that in some circumstances, like this, it can be the bicarbonate ion. That bicarbonate ion can also end up as an acid where it donates like this, or it can end up as a base where in the other circumstance, like maybe plus, this is not going to go well. So let me write it just one more time. Right here, HCl, 3 with a minus plus HCl, then could accept like this, like that. Now, under these two circumstances here, then you can see that there's a difference, and the difference is that here it's an acid because it donates the proton to the water, and here it's a base because it accepts the proton from another acid. So here I have an acid and here I have a base for HCO3. That's just one example of an amphiprotic species or molecule. Just letting you know that that can happen. What happens when acid dissolves in water? I just went through all this. Here's HCl. The H and the Cl split up 100% of the time. The H goes with the water to produce a hydronium ion, and the Cl stays separate. Okay, conjugate, there we just discussed this. I went too far ahead. Here's my acid conjugate base pair, and here's my base conjugate acid pair. Okay, that's how we keep them separated. Acid and base strength. So when something is a strong acid, then it's a negligible base, which means that it's not much of anything. If something is a strong base, then it's not, definitely not a strong acid. Okay, so that's all that means. You can see where strong comes in down here for base, like this, and we'll talk about pH in a second. And then you can see all the different weak acids and weak bases, and then strong up here for acids then. Okay, let's keep moving. So substances with negligible acidity do not dissociate in water. So that means that something with a strong acidity, like HCl, breaks up into H plus Cl minus 100% of the time. Okay? Another way to write this, of course, would be just like how I wrote it before, which would be with actually showing the H2O and then tagging that on like that. And that still happens 100% of the time. This would be the Arrhenius, this would be the Brownstead-Lowry way to show how the strong acids dissociate. So if it's not a strong acid, if it's a weak acid, then it tends not to dissociate in water very well at all. So even weak acids such as like carbonic acid. Carbonic acid does something like this. Less than 1% of the time. So that acidic bite that you taste from carbonic acid is really a very, very weak acid. Even though we know it's an acid, you can see that if that happens very little, like very low part of the time, then most of my reactant is still looking like H2CO3. That's what this means. Substances with negligible acidity do not dissociate in water, and those that are weak acids do not completely dissociate in water. not like our strong acids do. So what are the strong acids? You may want to write this down somewhere. Let me just list them for you here. So for strong acids, in case you don't have this written down, it's actually very important to know the strong acids because these are the ones that break up 100% of the time. So of course it's HCl, HNO3, which would be nitric acid, H2SO4. These three are the most common. And then we get into ones like, if HCl is one, HBr and HI, as in hydrobromic and hydroiodic. And then we have a couple more for HClO3. Chloric acid is a strong acid, and of course ClO4. So perchloric acid is the strongest acid. And I believe that's all the ones that fall into the category of being strong acids where they dissociate 100% of the time. Dissociate simply means they split up into their ions in water 100% of the time. Okay, these all will do that. Yep. Okay. Please get a list of these so you know what they are, because if you see something that is not a strong acid, you recognize that by knowing what the strong acids are. Here's a couple of them that are very common, but these are not strong acids. Okay, this is the one that makes vinegar. This is acetic acid, carbonic acid, you know what that is. That's AR. And this is phosphoric acid. Your body uses this. Okay, so these are all weak acids, which means that we're going to talk about weak acids later on, 16 point, blah, blah, blah. Okay, I think we're just about done with this section. Acid-base strength, I just talked about that, lies very far to the right for the K, which means K is much, much larger than 1. Weak acids are different, though, and we'll talk more about weak acids. So acetate is a strong base, stronger than H2O2, so the equilibrium favors the left-hand side. Okay, so that means that the acetate here does not, and that should be, I'm not sure why that is not written in there. That should be acetic acid plus H2O2, and then produces this over here on the other side. So please make that change. Okay, good. That's 16.3, and that's where I'll stop.